Let's continue to look at neural networks. So here is the AlexNet you have seen in last week, which has 5 convolutional layers and 3 fully connected layers in the middle, and an input image, and 1,000 way softmax as the output. So to understand such a complex architecture, let's look at the basic unit. Let's start with the machine learning process. So firstly, for machine learning, we need to have training data, typically labeled data with input X and label Y. For example, in a simple face classification task where we just need to detect a face to tell what is a face and what is not a face. And next, we need to choose a decision function, or we need to choose the model so that we can estimate a y from a x. That is to estimate an output from an input. So this is the forward pass. For example, in linear regression, we use a simple linear combination, and in logistic regression, we use the sigmoid function, and in neural network, we use the multiplication of weights with plus bars through multiple layers. And we also need to choose a loss function. So this is a metric to measure how good is the estimation. So typically, this will be a loss comparing the estimated output label with the ground truth label. And examples include mean square error for linear regression and cross entropy for classification. And after having the decision function and the loss function, we need to define a goal which gives us the objective function to optimize our model parameter theta. To obtain the best estimation of our model parameters theta, we need to train or optimize our model using some optimization method, such as stochastic gradient descent. So what it does is basically take small steps in the opposite of the gradient. Therefore, we need to compute the gradients, and these gradients are computed through back propagation. And nowadays, we use automatic differentiation. So this is a very familiar model of linear regression. So in this case, we get the output y from the input x through a linear combination. Therefore, the activation function is simply itself, right? So there's no transformations except the linear weighting. And what if we design a neural network using multiple linear regression? So for example, we have the first layer as a linear regression, and also the second layer as a linear regression, right? So we use linear neurons here, and also linear neurons here. So what will happen when we have such a multi-layer network? Actually, in this case, nothing special will happen because the product of two linear transformations is still a linear transformation. So here is some reference derivations, and you can try to work it out. But when you cascade two linear transformations, what you obtain is still a linear transformation. So no matter how many layers you put in between, effectively there's only one linear transformation from the input to the output. So effectively, there's only one layer and one transformation, no matter how many linear layers you put in between. Therefore, we have to use some kind of nonlinear transformations. Let us look at our familiar logistic regression model, which has a transformation like this. Okay? So it has this is a nonlinear transformation. And if we put logistic regression in sequence and to cascade logistic regressions, we obtain a logistic regression neural network. So here is an example with three input of age, gender, and the stage of, for example, a brain cancer. So these are sometimes called independent variables. So they are the input variables. And we will use some ways to combine the input, and this combination will be sent to a hidden layer and then pass through an activation, a sigmoid activation function. And the output of this unit or this neuron is then multiplied by another weight, and they are combined in another unit or another neuron, and then apply another sigmoid activation function to obtain the output, which is also called dependent variable. So this is the prediction, or we also call it estimate or the target. For example, the probability of being alive after 1 year or after 5 years or 10 years. So this becomes a prognosis, disease or cancer prognosis predictor. Right? So that is some very basic, very simple neural networks. In the next session, we will look at what we have learned, what is the decision boundary, and what are the features learned by neural networks.